morning.
Good morning.
Good morning.
Thank you. Hi, it's great to see you all, bright, shiny faces. Rebecca Higgins, your other co-chair. I get the distinction of introducing our next speaker this morning, who is Dr. Bridger Ruyle. Dr. Bridger Ruyle is a postdoc fellow at Carnegie Institute for Science Department of Global Ecology at Stanford. His research combines remote sensing and geospatial analysis to study the impact of climate change on riverine water quality in the Arctic. Previously, he received his master's in applied math and PhD in environmental science and engineering from Harvard. His dissertation research focused on developing novel analytical and statistical methods to study the biogeochemistry of PFAS contamination from ITRC, with an emphasis on PFAS precursors. Shout out to the PFAS crowd. Big day, right? At Harvard, Bridger also served as the Chief Academic Officer for over 400 undergrads at the Dunster House's interim Alston Burr Resident Dean. So, welcome Bridger. Thank you very much for honoring us with your presence today. This is a wonderful network of folks that Bridger has here in California working on AI and machine learning. But it's not just here in California, it is also in the country. So I hope you all enjoyed his talk this morning. Welcome.
Thank you, Rebecca, for the introduction, and I hope I can shed some light under the hood on this, in this talk about how some of these AI tools actually work in practice. So to give you an overview of what I'll talk about today, I'm going to give a brief introduction to PFAS and important PFAS point sources, and then I'll jump into two different applications of AI for PFAS, biogeochemistry and source attribution. The first is using Markov chain Monte Carlo algorithms to quantify precursors, and then the second application using random forest models to identify groundwater wells that are susceptible to contamination. And I already got an introduction, that was really nice, but I do want to also highlight that I am in the final stages of finalizing a contract with a university where I'll start my own lab as an assistant professor, and I'm very open to collaborations and working with states. I've done so in the past, so if there are interests, please feel free to reach out to me. Okay, so to jump in, just give a brief intro to the universe of PFAS. PFAS, or per and polyfluoroalkyl substances, are a subclass of organofluorine contamination that includes a lot of different complex chemistries. Okay, so I've drawn a dotted box around the universe of PFAS because what is a PFAS depends on what definition is used. The most expansive definition for PFAS include any molecule with a perfluoroalkyl moiety that is a CF3 or a CF2 group. This is the definition used by the OECD, which is much more expansive than definitions used in the United States. Under any of the definitions, compounds like you see on the left are considered PFAS, but under more expansive definitions, you start to include other compounds like the one on the right that have only a singly perfluorinated group. And I just want to highlight that which definition you pick will have a really big impact upon policy and engineering solutions, because as you start to expand further and further definitions, you start to talk about other compounds like agrochemicals and pharmaceuticals. So when we talk, regardless of definitions, there are still hundreds to thousands of individual PFAS molecules, which makes studying them incredibly difficult. So when we talk about the threat of PFAS contamination, not all molecules are created equally. We're particularly concerned about a subclass of PFAS called perfluoroalkyl acids, and today the US EPA announced their drinking water MCLs for 6 perfluoroalkyl acids, most of them being regulated under 10 parts per trillion. And they'll be given, I think they said they announced that they'll give utilities about 5 years to comply with this new regulation. So from nationwide monitoring studies, we know that the most significant sources of PFAS contamination include the use of firefighting foams, or AFFF, manufacturing, landfills, and wastewater discharges. Previous studies have estimated that drinking water contamination is likely to be exceeded in the drinking water for about 18 to 80 million Americans. This number totally does not consider the about 50 million Americans that rely on private wells, which I'll talk about later on this talk. But I think actually today the EPA also announced estimates that they expect between 6 and 10% of facilities serving 100 million people to exceed these new regulations. So all in all, urgent action is needed to characterize discharges and understand the fate and transport of these compounds released from these point sources. So how do we actually measure PFAS contamination? Standard methods rely on liquid chromatography, tandem mass spectrometry. This technique shown on top characterizes the regulated 6 PFAS along with about another 24 or so compounds, mostly other perfluoroalkyl acids. However, when we look at mass budgets from important point sources and compare them to proxies for total PFAS, such as extractable organofluorine, which can be measured using combustion ion chromatography, what we see in both cases for firefighting foams and wastewater, that we end up missing most of the organofluorine that is discharged from these point sources, indicating that these standard methods that focus on about 24 or so compounds is just very insufficient to understand what is actually present. So, looking at these major important missing gaps, we have to ask the question, what are we missing? And as I'll show later on, a lot of what we're missing is in this outer sphere of PFAS. These are compounds that have many perfluorinated carbons, but also, many also unfluorinated carbons that can undergo chemical or biological transformations in the environment to produce perfluoroalkyl acids. So I'll talk about 2 different applications of AI in this talk to help address the issue of the missing PFAS that we see from these important point sources. The first application, as I mentioned, is using Markov chain Monte Carlo for quantifying PFAS precursors. And then the second application is looking at once we have an understanding of the perfluoroalkyl acids, which private groundwater wells may be susceptible to this contamination. So, as I mentioned, we are missing most of the precursors or polyfluoroalkyl substances in standard methods. And this is because we lack analytical grade standards for the hundreds to thousands of individual precursors, meaning that we cannot measure them using liquid chromatography, tandem mass spectrometry directly. We know from high-resolution mass spectrometry that precursors generally come in 2 different flavors, depending on their manufacturing origin. One of the origins shown on the left is the fluorotelomerization process, which will produce precursors that have a long perfluorinated chain attached to typically 1 to 3, but most oftentimes 2 hydrocarbons, and then a functional head group. The other group of precursors is produced by the electrochemical fluorination process, and this includes a totally perfluorinated carbon chain attached directly to a functional head group. There we go. So, for a while, for about a decade now, we've been able to indirectly quantify precursors using a method called the total oxidizable precursor assay, or the TOP assay. In the TOP assay, we generate hydroxyl radicals from persulfate, which can oxidize the non-fluorinated carbons within a precursor and convert them into perfluoroalkyl carboxylates, or PFCAs. PFCAs are a member of the perfluoroalkyl acids, which we can then measure. So we take a sample, we oxidize it, and now we can get a proxy for the amount of mass that was precursors. But we don't actually know the original concentration of precursors, we just know what the precursors produce. We also know that precursors of different chain lengths and manufacturing origins have unique yield signatures. So the fluorotelomere precursors produce this range of PFCAs upon oxidation, while the electrochemical fluorination precursors tend to produce the perfluoroalkyl carboxylate with one less perfluorinated carbon than it had originally. So this is great when we just have maybe go into the lab, take a precursor, spike it, and we can measure a mass balance. But what happens when we go to a real environmental sample? The top assay can give maybe confusing and more difficult to interpret results. And that's because PFAS, and especially precursors, are oftentimes found in complex mixtures. So I'm showing you, for example, a profile of the top assay from a firefighting foam that was produced by 3M called light water, which was used historically at many military fire training areas and airports across the country. And you can see that the profile here doesn't exactly look like any of the two profiles on the previous slides. And we can't necessarily turn to material safety data sheets to help us gain any further insights upon the composition of original precursors that are present, because a lot of the times these MSDSs don't even acknowledge that these products contain PFAS. So to elucidate the composition of precursors in real-world samples, we can turn to Markov chain Monte Carlo algorithms to help us decipher this complex pattern of PFCAs that are produced within a sample. This is done by combining the known yields of precursors based on their number of perfluorinated carbons and their either electrochemical or fluorotelomerization structure with measurements in a real sample. And before I get into the math, I just want to say that we go from this unknown, which is the unknown concentration of precursors in a real sample, to an inferred or estimated concentration of precursors in this sample. This is an intermediate step which could then be later on followed up with direct analysis, where we can target individual precursors later on. So from this question, we can ask, what's the probability of original precursor concentrations, which I've given the nomenclature here A, given by the measured yields in the top assay, which I've named here as B. And this sets up a classical Bayesian inference problem. For those of you who maybe remember from college statistics, this is the equation for Bayes' law. And when we run this algorithm, we can produce an inferred distribution of precursor concentrations, which we see on the right. So how to interpret a plot like this is on the x-axis we have the concentration in log space of individual precursors grouped by the number of perfluorinated carbons in their manufacturing origin, which again, the number of perfluorinated carbons and the structure of the non-fluorinated substituent are the two most important properties that will dictate the fate and transport of these chemicals in the environment. And on the y-axis, we have the kernel density, and this is an estimate of how probable a precursor occurs at a specific concentration. So when we have a high peak, we say that, for example, this peak here, C6 electrochemical fluorination precursor is highly probable to occur at this concentration, whereas in these lower peak regions, we say it's highly improbable that it would occur in the sample at this concentration. And this is the result for the 3M foam, which we know used the electrochemical process. So we can see this algorithm is correctly identifying that most of the precursors here are electrochemical fluorination based. So to give you a brief under the hood of what this looks like, because there's some interest in how these algorithms actually work, when we break down Bayes' law, we can break this up into 3 different components. So as I mentioned, here in the equation, A represents the concentration of precursors, and B represents the yield that you can actually measure of PFCAs. And the equation on the left-hand side is the result, or in math speak, the posterior. And that is proportional to, on the right-hand side, the likelihood of the result based on the data, or the probability of B given A, multiplied by the prior, or what we know about the result before we look at the data. So how do we actually run an algorithm? So first, the algorithm will propose a random combination of precursor concentrations. So we're going to guess the solution here, A. Once we guess the solution, we're going to calculate the prior of the solution. So this will depend a lot upon what we know about the result before we start running the model out. So say we know nothing about our result. This would be what is called like a very data-driven result process. We could give a uniform prior, which means that pretty much anything is equally likely to happen. On the other hand, we could actually say that we know a lot about the result before we look at the data. In this case, this is a sort of expert allocution or expert knowledge application of MCMC, and we can give a very, very constrained prior, where we say it's highly likely to occur at this concentration and very unlikely to occur at any other concentration. Typically, how I've been using this, I've been using more uniform priors to really let the data speak for itself rather than try to enforce a solution upon the system. So after we calculate the prior, we then turn to calculating the likelihood. And how the likelihood is calculated is we take the proposed precursor concentration A, we artificially oxidize it using the known yields to create a hypothetical distribution of PFCAs, which here I've labeled as B star. And then we can calculate the likelihood by comparing the difference between the measurements, which are B, and the artificially oxidized result, B star, using some sort of like least squares estimation process. So to calculate the result or the posterior, we then multiply the likelihood and the prior together, and then we repeat this multiple times to form a distribution. So here, this is many different multiplications of likelihoods and priors for many different proposals, and what you see on the bottom is a distribution of the results. And typically, once we have a results distribution, we can then estimate central estimates, like what is the median or mean, or what's the standard deviation. So not only do we get information about saying like what is the concentration of precursors, but we could also say how certain are we that a precursor occurs at this concentration, and uncertainty quantification being especially important for regulatory purposes. So what happens when we add the concentrations of inferred precursors into a PFAS mass balance for the firefighting foams and the wastewater treatment plants? So as a reminder, if we're just looking at the regulated PFAS, we are talking about, in a lot of cases, less than 1% of the PFAS that is present in these products. But when we add in the method to estimate precursor concentrations from the top assay, we see that we're actually much better able to predict one-to-one the proxy concentration for total PFAS, in this case, extractable organofluorine. And what we find is that depending on the foam, precursors are making up between 50% to over 99% of the total PFAS in these products, and at wastewater treatment plants, they're making up about 3/4. So while there is a really big focus on these terminal compounds that are very important from a health context, these precursors can transform in the environment into these same compounds. So it's critically important to start considering these compounds, discharge, and their biogeochemistry in order to really understand and ensure that we're providing safe drinking water. So I want to just highlight some applications of this. The first application will be for source attribution, a very popular technique for statistical fingerprinting is principal component analysis. And what happens in principal component analysis is you can measure, say, a suite of dozens of PFAS. So you're in a potentially 20-fold dimensional space if you have 20 analytes. And you want to try to reduce that into some characteristic signatures. For plotting purposes, it's oftentimes best to try to reduce it into 2 dimensions. and we can try to see, can we separate different signatures of PFAS depending on if they came from, for example, firefighting contamination, or if they came from wastewater. And so some colleagues and I at UC Berkeley looked at the inclusion of the top assay and then further precursor quantification from the top assay to see if we can help improve and separate different unique sources. So we are looking here at wastewater treatment plant influent and effluent in orange, groundwater and surface water contaminated by AFFF in blue, and landfill leachate in green. And when we look at just the perfluoroalkyl acids, we can't actually come up with a unique fingerprint from any of these sources. So basically saying that a lot of times the characteristic composition of the perfluoroalkyl acids is not unique. And I think this was emphasized maybe yesterday in the CERTA talk as well, showing that as you go age a sample or go further from the source zone, you oftentimes get a funneling into the same compounds, and you really maybe lose a distinct source signature. So when we include just the increase of PFCAs from the top assay into this PCA approach, we're starting to now be able to separate sources with a unique fingerprint from landfills, but there's still an overlap between wastewater treatment plants and firefighting foams. That's shown in the middle, and then on the far right, we can see when we take the MCMC algorithm to quantify precursors, we're now able to fully separate and distinguish PFAS contamination by source. And what we can see, not only is there characteristic fingerprints like firefighting foam contamination in the environment being enriched in PFAS, PFHXS, and C6 ECF precursors, which can be transformed into PFHXS. But we can now also start to see impacts of like biogeochemical processes as well, where we see groundwater, which is further to the left on this diagram, more characteristically enriched in precursors, versus surface water, which is older, being more characteristically enriched in the terminal perfluoroalkyl acids. We can also use this in the context of fake and transport modeling itself. A lot of my PhD research focused on a contaminated site, Joint Base Cape Cod in Massachusetts. And here is a conceptual model of PFAS contamination at the fire training area. And as I mentioned, these firefighting foams are highly enriched in precursors, so running models that are only considering perfluoroalkyl acids is potentially going to miss many important processes like precursor biotransformation and precursor retention in source zone soils into the signature of perfluoroalkyl acids that can be measured in downgradient groundwater. And some of the work that I've shown is that actually precursors are responsible for sustaining entirely concentrations of PFBS beneath the fire training area today, and is responsible for most of the PFHXS below the fire training area today as well. And that these half-lives, although very small, corresponding to maybe several decades in the environment, because the terminal compounds are much more mobile, they can be quickly flushed through the system, and so it's these highly sorptive and retained precursors that are then contributing to the ongoing and slow stream of contamination that we observe potentially decades after the last use of firefighting foams. All right, so turning to the second application of AI, this is using random forest models to identify private wells that are susceptible to PFAS contamination, and I'm going to focus on a case study in the state of New Hampshire. So groundwater wells are an important source of drinking water across the United States, with about 40 million people relying on them nationally, and very important in the state of New Hampshire with about 500,000, or about half the population, relying on groundwater wells. And unlike drinking water utilities, which have a lot of money, or relatively have a lot more money to monitor these groundwater wells oftentimes are totally unmonitored, they're oftentimes private, and would be up to the owner to perform testing. And so to better understand which anthropogenic and hydrogeochemical parameters make groundwater susceptible to PFAS contamination, we partnered with the state of New Hampshire to analyze a data set that they collected between 2014 and 2017, which included sampling of about 2,000 wells across the state. And I've shown here results of whether or not PFAS were detected or PFAS were not detected in these samples. The detection limits were right about 5 nanogram per liter, so detection versus non-detection is also now sort of a proxy for above a hazardous level or below a hazardous level. And in all, about over 15% of wells had detectable levels of 5 different PFAS that we looked at. That's 4 of the perfluoroalkyl carboxylates and 1 of the perfluoroalkyl sulfonates PFAS. So to parameterize these machine learning models, we tried to relate anthropogenic and hydrogeological information to whether or not we observed a detection or a non-detection. So the input data were included distance to major industries within a watershed, and for New Hampshire, the major PFAS emitter is a textile manufacturer in the state, but there is also airports and military bases and plastics and rubber manufacturers. And then on the environmental side, some of the predictors that we looked at included bedrock type and depth, soil properties, and then on the hydrological side, we looked at precipitation, recharge, and the groundwater table. And also looked at soil properties like percent clay or fraction of organic carbon. So the question that we asked is, can we predict the occurrence of PFAS from the distance to point sources in the hydrogeology? And this sets up a binary classification problem. So binary as in, do we have a detection or do we not have a detection? And some of the binary classification tools that are popularly used include logistic regression, which is not an AI or ML technique, and then random forest machine learning. So I want to also bring up that there was a question on Monday about why choosing random forest over some other binary classification machine learning tools like gradient boost or support vector machines. And I think there is really important to understand that these tools, even though you can download them, use them in Python sort of black box, that there are important domain considerations to choosing which model to use. And I think oftentimes we'll find in environmental data sets that random forest is probably one of the best techniques because things like gradient boost can be highly sensitive to small data sets and introduce a lot of errors. When we're talking about thousands of samples, traditional machine learning is oftentimes considering millions or billions of data points, which just will never be possible in environmental applications. Or on the other hand, things like support vector machines, which oftentimes when we're dealing with mixed predictors, that is, sometimes the predictors we're using are continuous variables, like the amount of precipitation, but maybe sometimes the variables are categorical, like what is the soil type. It's those types of methods don't really perform well when you have mixed input data. So it is really important to understand the strengths and limitations of each different approach and to talk to applied math experts when formulating these research questions and your specific needs. So just to give a brief on what logistic regression is. Logistic regression is in a sense, a linear regression technique. But instead of doing it on the y is equal to mx plus b, you're doing it on the logit function. And what you'll get here is each coefficient for each of the parameters that are included in the model. And you'll basically predict, based on the input parameters, If it's above a 50% threshold of probability, that means you say, yes, it's a detection here. If it's below 50% probability, you say, no, it's not a detection here. And we compare this to what the structure of a random forest machine model looks like, which is many different models run simultaneously, and in each of those models, nodes, and what connects each of those nodes, again, is the logic function. But in this case, there are many different branches and connections between each node. So you set up, on the logistic regression side, looking at exploring only linear relationships between predictors and the outcome, whereas on the random forest side, you're able to now come up with nonlinear relationships between predictors and the outcome. And what happens in random forest models is that you instantiate a number of different forests. Each of them will come to an outcome separately. So say you have 10 forests, maybe 6 of those forests will say, yes, there's a detect. 4 of them may say, no, it's not a detect because these are probabilistic models. And then you can average them all together and say, okay, the majority of the time the models predict that there is a detection, and therefore you go forward and attribute that to a positive detect. So also to give you a little bit of a sense under the hood of what's actually happening, typically we'll split a data set into 10 or maybe 5 equal parts, and you really want to make sure that how you split data between training and evaluation is done in a way so that you can get accurate performance metrics. In this case, we split the data set into 10 equal parts and ran the model 10 times using basically a 10-fold cross-validation. So what you do is you use 9 of the 10 data sets as training data and 1 of the 10 subsets as evaluation data. And then you repeat this 10 times, with each of the subsets used as evaluation 1 time, so that you can get a sense of how confident you are in your predictors. And these models have a lot of different hyperparameters, like the number of trees that you use to make a decision, the number of layers within a tree, or the number of nodes within a layer. And these all will impact the outcome of your model. This is typically done using hyperparameter tuning with environmental data sets that are usually in the thousands. Grid search is a very easily accessible tool that can be done sort of out of the box in a lot of these algorithms and won't take up very much time given the relatively small size of the data set that you are looking at. And then on the evaluation side, the things that we're going to look at in terms of model performance include true positives, so that is if the model predicts that there's a detect and the data actually is a detect, a true negative, a false positive, and a false negative. And oftentimes how these models are then compared is a measurement called the area under the receiving operator curve, or the ROC. And what the